Hello everyone, my name is Vitaly and I work for Red Hat, and at Red Hat I'm usually responsible for RHEL as a guest efforts like running RHEL guest on third-party hypervisors and public clouds. And here next to me is Tianyu from Microsoft. Can you please introduce yourself?
Sure. I'm Tianyu. I'm from Microsoft. I'm working in the Microsoft Linux kernel team, focused on the network virtualization improvement now. Recently, we introduced a lot of Enlightenment feature for network virtualization, and we also focus on the I/O performance for the network virtualization. Okay.
Yeah. So, like a year ago, I got dragged into the nesting space. I was testing Hyper-V, and I thought like it would be cool to try running not only Linux on Hyper-V but also KVM on Hyper-V. Would it work? I tried, and surprisingly, it worked. So today we are going to talk about running KVM on Hyper-V, the current state of affairs, like what we've done over the last year, and what challenges are ahead. And my usual caveat when speaking about nesting is that it's really, really easy to confuse the audience when talking about nesting. It's really easy to confuse yourself, right? So if you're not confused, you're not paying attention, guys. Okay, so let's start with the terminology, and for this talk, we're going to be talking about this simple setup when you run KVM on top of Hyper-V. As you know, Hyper-V is a type 1 hypervisor, which means that it's more similar to Xen than to KVM. It has a separate hypervisor, and then its management domain, like root partition, is a Windows partition. It runs already inside the guest, and as level 1 guest, we will have Linux running with KVM, and on top of that, we will run our level 2 guest, which will be Linux for this talk. So, the main question is like, why doing this? Why bothering, right? And yeah, so there are several reasons for that. The first one is, and probably the main one for running on Hyper-V, is Azure. So we have this second biggest cloud in the world, right? And it runs on Hyper-V. And the hypervisor there is basically the partitioning hypervisor, if you think about it. So if you run a big enough instance on Azure, you're not doing something like shared core or like memory overcommit. You will always have your own resources there. So it's very reasonable to try to run whatever workload you want there, including virtualized workloads. And for example, some instances there have hundreds of CPUs. They have like terabytes of memory, literally, and you may want to actually partition them for several different use cases, but still stay on the same instance for example, economical reasons. The other reason to try this is because of these new secured containers efforts. And yesterday there was an interesting talk by Eric Ernst and KY. And if you haven't been there, I encourage you to watch the recording. They talked about running kata containers, and when you run them, this includes, that puts your container in a VM, and if you are running already in a cloud, for example, on Azure, that means that you're actually running nested. The other non-obvious reason to do this is that we are also interested in running Hyper-V on KVM. And for that, we're implementing also these enlightenments which are required to make them perform well. And we would like to test them, for example. So it would be really helpful if we can have both server and client implementation. Well, and of course, when we look at how things are done on Hyper-V, we get some inspiration, and we do similar things on KVM. For example, Wang Li did PV APIs inspired by our work for Hyper-V. So over the last year, we've done several things, and I'm going to walk through them and quickly explain why these things are important and what we've done. Yeah, so the first one is going to be like the clock source, then Enlightened VMCS, and then Tianyu is going to talk about PV-EPT invalidation. So the clock source. So some applications want to know what time is it now, and they want to know it very frequently, right? So they keep doing these requests, trying to figure out the current timestamp, and we want it to be as fast as possible. And for that, KVM and Hyper-V, they use different technologies. In KVM, it's called KVM clock. In Hyper-V, it's called Hyper-V TSC page. Both use the same idea. It's basically a page which is shared with your hypervisor, which has two numbers. It has like a multiplier and an offset. So you get your TSC reading, and TSC is, for who doesn't know that, is like a register in your CPU. So you can read it very fast even from your software. You don't need to go like into kernel mode for that. So you read it, you multiply, you add, you get the answer, like what time is it now? And it all works both for KVM and for Hyper-V. But when we are running nested, it didn't work. Because in KVM hypervisors, you will get stable clock source for your guest only when your main clock source is TSC. And TSC page Hyper-V is not this one. So yeah, what we've done, we've enabled it. So we explained to KVM that Hyper-V TSC page is an equally good clock source, and it works. After that, you get stable clock source in your level 2 guest. So you can read the timestamp with the same, basically, cost, at the same cost. But there is one problem with that. So your level 1 guest with its all level 2 guests can migrate. And what happens when you migrate? And that's actually the reason why we have these clock sources, and we are not exposing raw TSC. The reason is that when you migrate, your TSC reading changes. First, the offset is different. Second, the frequency is different. So your hypervisor can adjust these values for you. If you're using this PV clock source like KVM clock, you will again do the multiplication, addition, and you will get the correct result. But what's going to happen to your level 2 guest? So Microsoft came up with so-called Reenlightenment feature. They like this word, right? So what happens is that level 1 migration happens usually like transparently. But if you're running your own guests, then you actually need to be aware of it. And the feature they've done is that you can enable the feature, so telling your level 0 hypervisor, which is Hyper-V, that you're actually interested in the information about migration. So when you migrate, your TSC access becomes emulated. And the hypervisor tries to preserve the frequency and the offset. So from your point of view, and the most important from your guest's point of view, nothing changes. But in level 1, you get an interrupt. You're supposed to stop all your guests, adjust their TSC pages. You already know the new TSC frequency, and disable the emulation and run them again. So we have this now in KVM. It works. So it's possible to migrate KVM with all its guests, and level 2 clock sources will remain stable. The other feature I wanted to talk about is Hyper-V Enlightened VMCS. So you all probably know how virtualization is implemented on Intel platform, right? So basically how you run a virtual machine on Intel, right? You create a structure in memory, like page size, and then with special instructions you set the required state, like registers and other stuff, and then you tell your CPU, please run this. This is my virtual machine. Then it will run natively on your CPU, and only when some special event happens, it will get back to you, and you can analyze the state again in the structure and do something with it. Modify it and continue executing. So when we are talking about nesting, how would it work? Level 1 hypervisor thinks that he can create such a structure and he can do something with it. But actually, he doesn't own the structure. It's still level 0 who owns it. So all the VM write, VM read accesses, and that's the instructions you use to actually edit the structure, because you don't know it, right? It's hidden from you. It's there in the memory, but you don't know where these fields are. So all these VM reads, VM writes will go into level 0. It will emulate them for you, will get back to you. It's not going to be super fast. So they came up with the shadow VMCS idea. I'm trying to speed up a little bit. And with shadow VMCS, basically there is a structure in memory. It is a hardware feature. And level 1 hypervisor can access fields there natively without doing VM exits. But the problem is when we are trying to then execute this level 2 guest from level 0, we need to merge the information. So we need to read the whole structure, merge it with our understanding of what's allowed and what's not for the guest, and continue executing. So from that point of view, that's also not that fast as it could be. So Microsoft came up with this Enlightened VMCS idea, which is a software feature, and basically it exposes the structure of this VMCS from level 0 to level 1. So level 1 can access it with normal memory accesses, and moreover, there is an interesting thing there that you have a field which tells level 0 hypervisor which fields were changed by level 1 hypervisor. So if no changes were done, then it doesn't need to read the whole structure. It can read only what was changed there. So that becomes much faster, and that's the Enlightened VMCS. It basically, yeah, as I said, it says like, if you do like CPUID loop in level 2 guest, the feature will save you like 1,500 CPU cycles. We have it merged already for quite a while. The other idea, which is just an extension of the previous idea, is Enlightened MSR-Bitmaps. What is it? You have, as you know, Intel platform has machine-specific registers, and you sometimes want to access them. And when you're running a virtual machine, there is a bitmap which tells which MSR accesses you're interested in and which you are not. When you're running nested, it's the same story, but now you have like 2 levels of it. So this feature is basically, again, the same PV interface which tells level 0 hypervisor what was changed by L1. And using the feature, you can make accesses to these MSRs, which are the most important MSRs, which are being used when you switch between tasks, basically, between tasks and kernel. You can use them VM exitless. And it saves, again, a lot. So the third feature I want to talk about is EPT invalidation, and Tianyu is going to talk about it.
Hyper-V provides 2 kinds of the hypercore to flush the EPT TRBs. First, let's see how the general solution to flush EPT TRB in the bare metal in the network virtualization environment. Intel provides the invalid EPT instruction to flush the EPT TRB, but the instruction needs to execute on the target CPU and actually accept the EPT page table as the flush unit. That means if we want to flush the remote EPT TRB, we need to send the IPI to the target CPU. That will cause, if the L2 guest is running on the CPU, we need to force the L2 guest VM message and switch from L2 to the L1 and then inject the IPI. And the L1 hypervisor will execute the invalid EPT instruction. The instruction is emulated by the L0 hypervisor. So it will track back to the L0 hypervisor again. And finally, L1 hypervisor needs to run the L2 guest again. So it still needs to track back to the L0 hypervisor again. So you will find there are several jumps between the L1 and the L0 hypervisors. And otherwise, the whole process will be repeated for all the affected CPU. To reduce such kind of the overhead, Hyper-V provides the first hypercore. It's called the flash guest physical address space hypercore. The hypercore can help the L1 hypervisor to flash EPT TRB without the L1 hypervisor involvement. And this one single hypercore can work for all the affected CPU. So just one VNC to flush all the affected CPUs. The second hypercore, let's see how the nested EPT works. First, the target of the nested EPT function is to translate the LT GPA to the host physical address. But normally, the L0 hypervisor doesn't have the mapping between the L2 GPA to the L1 GPA. So it needs to shadow the L1's EPT page tables. How to shadow the page table? Normally, we'll use the write protect mode. But the write protect mode will introduce a lot of VMs if the L1 hypervisor changes the EPT page table very frequently. And finally, it still needs to use the flush instruction. So for such case, the Hyper-V provides the second flush hypercall, we call flush guest address list hypercall. The hypercall can accept the EPT page table and the specific address range list. That means the L1 hypervisor can use the hypercall to tell what edge has changed for the EPT page table in L1. So that can improve the flush efficiency, and otherwise we don't need to write protect the L1 EPT page table. So that can reduce the VMC caused by the modification of L1 EPT page table. Okay, that's the invalid EPT sections. Next, we also compare the data, storage performance data with the previous Enlightened feature and without the Xen. So in our test environment, we pass through the NVMe to the L1 guest and expose the NVMe via the virtual I/O SCSI from the L1 to the L2 and run FIO benchmark about 30 milliseconds. We compare the data when we use the version 4.18 and version 4.15 in the L1 guest. The average the I/O storage performance go up to about 17% in our test environment. Most contributions come from the MSR emulation and the VM read-write emulations. The MSR access has dropped about 39%, and with the Enlightened VMCS, all the VM read-write will not cause the VM exit. Yeah, okay.
Thank you. So now let's get to challenges. Direct TLB flush. There is a feature in Hyper-V which allows level 0 hypervisor to be utilized by level 2 to do its TLB flushes. Because how's TLB flush procedure done on Intel? Well, if you want to do TLB shutdown on other CPUs, you need to send IPIs there. The problem is that in virtualized environments, you don't really know if these CPUs are running or not. So it's more that when you are nesting, because it may happen that there is some other level 2 guest, or there is level 1 guest there. You don't know. But when you're doing TLB shutdown, you are sending IPIs there, and you are waiting for them to perform the shutdown. So that's why we have PV TLB shutdown for both like LinuxCon Hyper-V and LinuxCon KVM. But what happens when you are running nested? Your level 1 hypervisor doesn't really know if the particular vCPU is currently being executed or not. So it cannot really save much. And Hyper-V folks, they came up with the idea that you can send the request directly to the level 0, which will perform the request for you. It's great, but we face like a problem there. Hypercall conventions are very different between KVM and Hyper-V. In KVM, we use these registers. In Hyper-V, we use that. So the thing is that if we just enable the feature and try doing this, then a couple of KVM hypercalls which use like RCX for a parameter will be intercepted and executed as TLB flush hypercalls. Yes. So that's not going to work. So what are our options? Well, we can fully disable KVM-style hypercalls in KVM and only live with Hyper-V style hypercalls there. We have them implemented for Windows running on KVM. We can do that. The second is we can probably not do anything, right? And don't use the feature. May not be very good. We can also ask Microsoft to make their interface switchable to KVM style hypercalls. Weren't really successful so far. So yeah, for now the feature stays unimplemented just because of that, right? So we cannot enable with the current hypercall ABI. What else? Yeah.
Yes.
So
the more challenges for the nested virtualization, nested VMs I/O performance. Hyper-V so far doesn't support the virtual IME supports, so you cannot pass through the physical device from the L1 to the L2. Other side, so far the post interrupt cannot work with the nested virtualization on the Hyper-V. That means even we pass through the physical device to the L1 without nested virtualization enabling, will lose the post interrupt. The interrupt will arrive the L0 hypervisor first and jump and inject to the L1 the VM. So that will introduce a lot of overhead. To overcome such kind of challenge, we are evaluate the user space polling mode driver DPTK and SPDK to accelerate I/O performance for the nested VM. DPTK and SPDK, first they use the Xen polling mode, so it can reduce the interrupt overhead. And it will use the L2 guest memory directly for the DMA memory. So the data can arrive the L2 guest memory with zero callback.
Thank you. What are our plans? I did a very, very simple benchmark running tight CPUID loop in L2 when running Hyper-V on Hyper-V and KVM on Hyper-V. As you can see, we are worse, but not significant, like 20%. So I was going to take a look like what's going on and if it can be improved. So we reach like parity with Hyper-V and Hyper-V. The other thing is with the direct flash, we can try to send an RFC like disabling KVM hypercalls in KVM. Not sure if KVM maintainers will like such an approach, that in some cases Linux on KVM will use Hyper-V hypercalls exclusively. We're also working on putting the same features, the server side of the same features in KVM, enabling Hyper-V on KVM. So when it's done, we are going to enable testing. We'll be able to do that. So like in KVM unit tests, we'll be able to run all the VMix tests using Enlightened VMCS, for example. And then the SPDK and DPDK work Tianyu just mentioned. And we also have a new version of Hyper-V coming out soon, so let's see what it brings us. So thank you.
Thank you.
Any questions? Yes.
Let's make it quick, time.
Yes.
In your comparison, is 4.15 against 4.18 the kernels?
Yes.
Do we need, first of all, either enable anything special to get it if you have 4.18 and or any user space components to make use of that?
No. No,
so
it all works. Yeah, so
just new kernel
yeah,
in
if you run on Hyper-V, KVM will detect these features automatically. We don't have any enablement in user space for them. We don't require them. It happens automatically.
Okay, thank you very much.
Okay.
Thank you.
Thank you.